There's a lot going on in section 4.5. I don't think it would hurt to go ahead and take a look at that. Also, we're supposed to do 2 sections on Wednesday the 18th. So let's look at this. At least, I think we've seen maybe a couple of these type 1 exponential equations already. If we haven't talked about it in class, you may have seen this in the 4.1 homework, I believe, when we talked about exponential functions. My math lab tossed in some type 1 exponential equations. So let's officially see how we would go about solving these. F of x equals a to the x is a one-to-one function. We verified that. The graph passes the horizontal line test, so it's one-to-one. What it means is that there's a particular y value that's the y coordinate of some point on the graph. There's only one x value right there that'll give you that y value. So if this is y equals a to the x and a to the x power equals a to the y power, and they're giving us the same y coordinate, it means they represent the same x coordinate. X would have to equal y in that case. So if the bases are the same and the quantities are equal to each other, the only way that can happen is if the exponents are also the same. Seems like I should start with maybe a kinder, gentler example than the 2 that I have here. How about this? 3 to the x power equals 3 to the 4th power. What do you suppose x has to be? I think 4? Yeah, 3 to the 4th power is 81. 3 to the 4th power, well, there's no other power of 3 that can give you 81 as the answer. So x has to equal 4. We could use a similar tactic in example 1a and example 1b, except the bases as they are handed to us are not the same. It has to be the same base here as it is here. Now, although 9 is not equal to 3, 9 is a nice power of 3. 9 equals 3 raised to what power? 3 to the 2nd power. So what we can do is say 3 to the power of x plus 2 equals 3 squared to the power of 2x minus 1. So it kind of works our way toward writing them as powers of the same base. Just picking up the 9, putting a 3 squared down in its place, because 3 squared equals 9. Now, we want to clear the parentheses. In order to be able to use this one-to-one property of exponential functions, we have to have 3 raised to a power, and now it's 3 squared raised to a power. So to do that, we use the power rule for exponents. If we have a number and that's raised to a power and that expression's raised to a power, what do we do with those powers? We multiply, right? This is going to be 3 to the power of 4x minus 2. And then, if 3 to this power equals 3 to that power, the only way that can be true is if the powers have the same value. X plus 2 must equal 4x minus 2 in order for this to be true. So what's x? Four-thirds?
So you're subtracting the x from both sides.
Subtracting the x from both sides. Adding a 2 to both sides. Solving this linear equation. And so x equals 4/3. It would be a little bit of a pain to check this, and you might check it using a calculator. It would be 3 to the power of whatever 4/3 plus 2 is. Just putting the 4/3 in for x right there. 38.94 something. And then if you take 9 and raise it to the power of whatever 2 times 4/3 minus 1 is, ought to get the same answer if this is really the solution. And we do. So just a quick check there. It's not mandatory that you check these types of equations like the radical equations and other types of equations, but it's comforting sometimes, I think, to feel like we're on the right track.
So you just dropped your 3, like when you had when you subtract, you had 3 with the exponent x plus 2 and 4x minus 2.
Right.
And you just dropped your 3 to take care of your exponents only.
Basically, yeah, drop both the 3's. The exponential expressions are equal to each other, and they're the same base. So the only way they can be true is if the exponents are equal to each other. So you just set the exponents equal to each other. 3's go away. Similar sort of thing here, except 125 is not a super nice power of 25. It's an okay power of 25, and 25 is an okay power of 125. But they're both pretty nice powers of what number? 5. So take 25 and write it as 5 squared. And take 125 and write it as 5 cubed. And simplify. In the exponents, we don't have parentheses around them, but I don't think it hurts to observe that we should treat this as though they had parentheses around them, because we're multiplying a number by that, so we have to distribute that number across the parentheses. So this is 5 to the 4x plus 2, and this is 5 to the 3x plus 12. Since the bases are the same, we set the exponents equal to each other. And what's x? X equals 10. You can check this, but you get really big numbers on both sides. What we'll be doing is asking ourselves, is 25 to the 21st power equal to 125 to the 14th power? You suppose that ought to be true? 25 to the 21st power? I think in both cases, it's going to be 5 to the 42nd power, which is a ridiculously large number on both sides, but it is 5 to the 42nd power on both sides. This looks kind of rough, huh? Especially the B part. We'll do one that looks like the B part next time. But consider this. So how do you solve this? 4 to the x power equals 16. What's x? 2. X equals 2. How about 4 to the x power equals 64?
4.
Is it 4? 4 times 4 is 16. 16 times 4? 64. What about this one? 4 to the x power equals 32. It will be a fraction, definitely. What fraction? 2 squared to the x equals 2 to the 5th. 2 to the 2x equals 2 to the 5th. 2x equals 5. So what's x? 5 halves. Okay, so easy, almost as easy, not quite as easy. What about that one? 4 to the x equals 47. 47 is not a nice power of 4 at all. So what we'll do is we'll use logarithms. What I've done up here is I've taken the natural logarithm of both sides. Any logarithm will work, but it's helpful to use a logarithm that you have a button for on your calculator. So I'm going to suggest using the natural logarithm, because sometimes in the case of part F you have a base E, and it's extra nice when you have a natural logarithm and you're dealing with base E. So we'll say the natural log of 4 to the x power equals the natural log of 47. What the logarithm does is enables us to get the variable out of the exponent out in front, where we can work with it. The x comes out in front, and we have x times the natural log of 4 equals the natural log of 47. And that still looks a little bit on the awful side, because we have those ln's. But really, it's just a linear equation. All you do at that point is divide both sides by the natural log of 4. And then it's a calculator problem. Natural log of 47 divided by the natural log of 4. And I will mess this up if I try it otherwise, but just a word of caution. When you're dividing a natural log or any kind of log by something, make sure you close the parentheses. Otherwise, it'll divide the 47 by the natural log of 4 and then try to take the log of that. Won't give you the same answer. So close the parentheses. Natural log of 47 divided by the natural log of 4. And it's 2.7773 if we want 4 decimal places. So we would have expected it probably to be between 2.5 and 3. And it is 2.7773.